All right, welcome in. This is our final video for Chapter 4 material on equilibrium. Certainly not our last time thinking about equilibrium, but our last time in this chapter going through our equilibrium material. In this video, we'll use Le Chatelier's principle as a qualitative way to look at equilibrium without having to do any calculations. In our previous videos, we talked about the equilibrium constant expression. We talked about our ice tables and our calculation techniques for equilibrium. Well, now we want to step back and try to think about equilibrium once again, purely conceptually, without having to do any calculation. Our method for doing this is known as Le Chatelier's principle, which says if we ever have an equilibrium system, we can do something to disturb our equilibrium, but the reaction will proceed in a direction to regain its equilibrium. If you ever disturb your equilibrium, it will get back to equilibrium. In order to get back to equilibrium, we're going to have to kind of undo the change that was done, undo the disturbance. If we're thinking about minimizing disturbances, well, this could be a disturbance by adding chemicals or removing chemicals. We can change the pressure if we have a gas type system. We can change the temperature of our reaction. Right? We want to be able to handle all of these disturbances and be able to predict, well, if our reaction will go forward to counteract this, or if our reaction will go backwards to counteract this, or perhaps nothing will happen in response. We can start with an example. If we have this reaction of iron 2 oxide with carbon monoxide forming iron with carbon dioxide, this is a system that can reach equilibrium. Once it's at equilibrium, if more carbon monoxide is added to our reaction, this is a disturbance. Our reaction will try to undo that disturbance. Our reaction will try to minimize that disturbance, try to regain its equilibrium by, well, if CO is added, the reaction will try to get rid of that CO. And so our reaction will shift towards the right so that our CO turns into our products and we can be at that happy equilibrium state once again. We can think about why this is the case by considering our equilibrium constant. Our equilibrium constant, Kc, is a constant, and for this reaction, it's going to be our gaseous reactants and products, CO2 divided by CO. If we add some carbon monoxide to the system, well, then we are no longer going to be at equilibrium, and we'll have some reaction quotient instead of our equilibrium constant. Our reaction quotient will look like this, the same form as the equilibrium constant, but we don't have to have equilibrium concentrations for that Q. If we've added CO to the system, that will mean our CO is bigger than it was. Our value for Q is going to be smaller than our value for K. Remember what happens when we have a reaction quotient that's too small? Well, that means we're going to have to shift right in order to reach our equilibrium. We're going to have to do that forward reaction if our Q value is too small. So in some ways, this is knowledge that we already kind of had. Le Chatelier's principle is just a simpler way or a different way to frame it. Instead of having to do calculations for Q and compare it to our numerical value for K, we can just think about counteracting any disturbance that might come across our reaction. If we do something like adding extra CO2, this would be adding extra product. This would making our Q value too big instead of too small. And our reaction will have to shift left in order to counteract that. Adding reactants will do the forward reaction. Adding products will have to do the reverse reaction. We said we could also remove things. If we remove some CO2, well, getting rid of some products, our reaction will shift to remake it. If we're trying to remove some reactants, our reaction will have to shift forward in order to regain its equilibrium. Our last practice problem here If we have iron 2 oxide added, notice here, this is a solid. In our K expression, the iron 2 oxide doesn't actually appear in that equilibrium constant. This will have no effect, no change. And so this is how we can deal with adding or removing chemicals, changing the concentrations, and trying to regain equilibrium from there. We said we can also adjust pressure, or perhaps adjust the volume of our reaction. If we're changing the pressure of our reaction, well, we'll try to shift in order to counteract that. Try to shift either forwards or backwards to remove pressure. In this reaction, N2 plus 3 H2s at equilibrium with 2 NH3s, nitrogen and hydrogen form ammonia. If we increase the pressure of the reaction, can we do the forward reaction or can we do the reverse reaction in order to counteract that? Well, the key here is counting up the moles of gas in our reaction. We have 4 moles of gas on the left, just looking at the coefficients in our balanced reaction, right? The coefficients for gas phase chemicals. We have 2 moles of gas over in the product side. If we go with the forward reaction, that means we will use up gas. That means we'll have less gas. There's less gas on the product side, and so if the pressure is increased, shifting towards the product side can counteract that. Our practice problem, pressure and volume are going to be inversely proportional. And so if the volume increases, that will decrease the pressure of our reaction. So for all the reasons stated above, if we decrease the pressure in order to regain equilibrium, then we'll have to go back to the left. Our goal with Le Chatelier's principle is to make this a little bit intuitive without having to do any calculations. But if we want to do a calculation at least just once, we certainly can to make sure that our intuition is correct. So let's do that. Here is our expression for Kp. This is the equilibrium constant in terms of partial pressures. If we're going to change our pressure, we can compare our Q in terms of pressures to our K in terms of pressures, just like we did previously. Here's our reaction at equilibrium. Maybe we have 44 ATMs of PCl5, 4.77 ATMs of PCl3, 4.77 ATMs of Cl2. Our Kp value is going to be 0.516. All right, in this case, what happens if the total volume is cut in half? Well, if we cut the volume in half, that means we are going to double our pressure. Our value for Q in terms of pressure, well, it's the same expression, but now we're using these other values. So we can compare our Q value to our K value. Q ends up being much bigger than our K value. That means we're going to have to do our reverse reaction in order to reach our equilibrium, right? Our reaction will shift left. So mathematically, we can do this equation, right? If we're increasing the pressures, if we're decreasing the volume, well, in this case, our reaction will shift left. Is that what we would think intuitively with our Le Chatelier's principle? We can count up the moles of gas. We have 1 mole of gas on the reactant side, and we have 2 moles of gas on the product side. If we have more gas on the product side and we are increasing the pressure, well, we can go backwards to rectify that. We can do the reverse reaction to counteract that and get rid of some pressure. So yeah, Le Chatelier's principle does give us the same answer without any calculations. Fantastic. One last disturbance that we can consider when we are thinking about Le Chatelier's principle, we can start to think about temperature. When we change the temperature, we are going to actually change the value of our equilibrium constant. At different temperatures, our equilibrium constant does have a different value. As it turns out, there's a different pattern for how our equilibrium constant changes depending on the value of our enthalpy of the reaction. If we have an endothermic reaction, a positive value for delta H, then our temperature and our equilibrium constant have the exact same trend. Alternatively, if we have an exothermic reaction, temperature and the equilibrium constant have the opposite trend. What does this mean? Well, this means that for endothermic reactions, if you get hotter, that means our equilibrium constant is going to be bigger. That means we're going to have more products. If we're talking about exothermic reactions, well, as exothermic reactions get hotter, our equilibrium constant is going to have a smaller value. That means we're going to have more of our reactants. If you'd like a numerical reason why, well, there's an equation here. We'll get into this in, well, maybe a few chapters. But we said our goal here was to not have to do calculations, so we can purely just think about the trends. All right, the real answer for temperature and equilibrium constants, well, temperature changes the actual value of the equilibrium constant. We can have a shortcut. Our shortcut is to consider heat as either a reactant or a product. If we have an endothermic reaction, that means we have heat as almost like a reactant. If we have exothermic reactions, then heat is almost like a product. If we're thinking about it that way, we can go back to what we were doing for just chemicals. If you add a reactant or if you remove a reactant, a reaction will shift to counteract that. If you add a product or remove a product, our reaction can shift to counteract that. Once again, this is just a shortcut for heat. That's not actually what's happening, but it does give you the correct answer. So here's what this looks like. SO2 combines with oxygen to produce SO3s. This is an exothermic reaction. We can think about heat almost as if it's a product. For the reaction above, we are increasing the temperature. That means, well, we're almost thinking about adding a product. We want to counteract that. And so our reaction will shift left. This is our shortcut. It gives us the right answer. The reason why, the real answer, is that for exothermic reactions, if we are increasing the temperature, that means our value for the equilibrium constant is smaller. And with a smaller value of K, we're going to have less products at equilibrium. And with a smaller value of K with less products, our reaction will have to shift left. So, okay, we can see that it gets us to the same right answer, this little shortcut. It's good to know the real mechanism for how this works, but the shortcut is a good way to get the answer quick. All right, we'll leave you with one last final practice question. Our goal is to make as much product as possible. Maybe we're trying to manufacture these products and capture them, produce them as efficiently as possible. Can we think about maybe 5 ways to do this as efficient as possible? And that will do it for our chapter 4 material. Right, thinking about an introduction to equilibrium, some calculations, and now in this video, some ways to avoid doing some calculations using Le Chatelier's principle. We will continue with equilibrium thoughts, but just in different contexts. So stick with us there. Hope to see you in the next video. Please let me know if you have any questions, and thanks for hanging out.